Hello and welcome to this video. Alright, so in this video we're going to go ahead and kind of get an idea of what's going on here with the equations that you guys are going to be using. Alright, so you're going to be working with two equations. The first equation is going to be E equals to H times nu. Okay, this is the Greek letter nu. It stands for frequency, and this is one of the equations you're going to be. So H times nu is equal to E. E is energy, H is frequency, Planck's constant, and nu is frequency. Talk about it in just a little bit. Second equation is C is equal to lambda times nu, where C is the speed of light. Um, Lambda is a Greek letter, like a Greek L, and it is the wavelength of light. And once again, nu is frequency. Right? So let's look at these real quick before we actually use them. So once again, E equals to the energy. And this is how much energy there is per photon. Okay, so these equations have to do with light and little packets of light energy called photons. And so E is the total amount of energy in that photon. Nu, I'll put it as, let me go ahead and get rid of that here. Nu, you pronounce it N-U, nu, is frequency. Right? You learned in the last video that light has frequency, how many waves per second. And usually the units are in either per second, waves per second, or hertz. By the way, the units for energy are in joules. Okay, joules are a unit of measure of energy that we use in the SI system, and frequency is per second or hertz. A hertz is a wave per second. So when the frequency is 1 hertz, that means it's one wave passing a certain point per second. H, I'm going to put this in a different color. H, I'm going to put it in red. H is called Planck's constant. Planck's constant, named after a guy named Max Planck, or Max Planck. And H is 6.63 times 10 to the minus 34th joules times seconds. Okay, and that's so that the units will kind of work out. Okay. Basically, for every frequency, for every hertz, there's 6.63 times 10 minus 34 joules. That's what Max Planck figured out way back in the day. And this is in red because it's a constant, which means that you always use this number. So see this right here, this H, always the same number, right? You don't have to worry about what H is, which means in this equation, there are two variables. The variables are E and nu, the energy and the frequency. And H is a constant. In other words, it's always the same number. So as long as you have one of the two, you can figure out the other one. Now let's take a look at the other equation. And once again, these are properties of waves. And since light is a wave, it would have these properties. How much each photon of a certain photon of light has, how much energy it's got, is right here. And it's related to the frequency. The higher the frequency, the higher the energy. That's what Einstein found. That's that the energy is proportional to the frequency. It doesn't matter how many photons hit you at one time. The amount of energy per photon is based on the frequency. Now the second equation over here, and I'll rewrite it over here, is, go ahead and change the colors back. C is equal to lambda times nu. And so there's a couple of Greek letters. And once again, we use Greek letters because sometimes we've only got 26 Latin letters. And so we, don't want to, we have more than 26 times 2, let's say 52 things that are variable in the universe. So sometimes we run out of letters in our alphabet, which is the Latin alphabet. So we use the Greek alphabet. Lambda looks like this. Looks like an A that I forgot to put a little mark across. Is, and I tell you how you pronounce that. Lambda. That is the wavelength of light. Okay. And usually the wavelength of light is in meters. Sometimes you'll get it in nanometers or something else, but you need to convert it in meters. It has to go in meters in this equation. Nu, once again, is the frequency. Is frequency. And once again, its units are either in waves per second or per second. It's understood that it's waves per second when you get per second, or hertz, one or the other. But they're the same. 50 hertz is the same as 50 per second, or 50 waves per second. So this looks like kind of like a V that's blowing in the wind to the left. Right? So the wind is blowing from the right to the left, and it's blowing it to. So this is a Greek. Actually, I think it's a Greek N called nu. This is a Greek L, lambda. And the C, and I'll go back and use the red color. The reason I'm using the red color is because it is also constant. C is the speed of light. So this is the speed of light. Actually, it's the speed of electromagnetic radiation. You can do these equations with any type of electromagnetic radiation, whether it be X-rays or gamma rays or radio waves. But it turns out that C has a specific value. It's 3.0 times 10 to the 8th meters per second. Okay, and every time you use this equation, C is always the same. You have two variables, lambda and nu. Those could change. So in this equation, there's three letters, but only two of them are variable. And the C is a constant. It's always 3 times 10 to the 8th, which means that if you know one of these two, you can calculate the other. Okay. So these are the relationships in anything that it has waves. And light has waves in it. And if you know the wavelength, you can calculate the frequency. If you know the frequency, we can calculate the wavelength. Same thing over here, previous. Once again, this equation right here has only two variables, energy and frequency. If you know the frequency, you can calculate the energy. If you know the energy, you can calculate the frequency because H is a constant. Okay, so let's do some sample problems. Okay, so let's try this problem that we have right over here. This says right here, calculate the energy of a photon with a frequency of 6.3 times 10 to the 13th hertz. So we want to look for energy. Oops, moving that around. Let me just go ahead and get the writing done here. We're looking for energy. These things here. We're looking for energy, and we're given a frequency over here. So remember that the equation is E is equal to H times frequency. This H right here is a constant. We already know it. It's 6.63 times, even if it was different numbers in the problem, the H is 6.63 times 10 to the minus 34th joules times seconds. Right? So if we want to figure out the energy, energy is equal to H, 6.63 times 10 to the minus 34th joules times seconds. That's your H, times your frequency. And your frequency here, you're told, is 6.3 times 10 to the 13th. So 6.3 times 10 to the 13th. And as I told you guys earlier, oops, let me go ahead and get rid of that. Hertz is equal to per second. And you know what? I'm going to go ahead and put the per second units in here because you're going to see that it's going to cancel out and leave us what we need. So we have E is equal to 6.63 times 10 to the minus 34th times 6.3 times 10 to the 13th. I guess hadn't noticed that, but I guess that the two numbers start with 6 point something. So 6.63 times 10 to the negative 34th multiplied by 6.3 times 10 to the 13th is going to give you 4.16. 4.16 times 10 to the minus 20th. So you're going to end up with 4.16. I did that on my calculator. Times 10 to the minus 20th. You'll notice that the seconds here are going to cancel out with the seconds in the denominator here. These guys cancel out with this. And then the only units that are left are the joules. So we're left with joules. And I told you earlier that, mentioned earlier that joules are units of energy. Okay? So basically that's how you do it. This is probably the easiest problem you're going to get in this. You're asked for the energy, you're given the frequency. You just multiply your frequency times Planck's constant, and that gets you your energy. Okay, so let's try a second problem. We'll kind of move things around a little bit. This question right here says, calculate the frequency. Let me go ahead and make sure that I have my pen working here. Calculate the frequency of a photon of light with energy 8.35 times 10 minus 19 joules. So we're still using the same equation because it's giving you, this case, you're given energy. We always have H, and we're looking for frequency. So how do we calculate this out? Two ways you can do it. Number one, you can just plug the numbers in. Remember, once again, H, as usual, as always, is 6.63 times 10 to the minus 34th joules times seconds. So that number is going to go in here. If you have energy, you can plug it in here, plug those two numbers in and solve for frequency. I'm going to show you a different way of doing it. Same thing, but I'm going to move the letters around instead of the numbers so we don't have to be dividing by all these big numbers with scientific notation in them. So we're looking for frequency, right? So what we want to do here is get frequency by itself, which means we want to get rid of H. So what we're going to do is we're going to divide both sides by H. By dividing both sides by H's cancel on the right side, leaving you with frequency by itself, and you end up with E over H there. So this turns into E equals, E over H. Let me get rid of all that. E divided by H equals to frequency. And you can turn that around. Frequency is equal to E divided by H. Now you have E, you have H. You can just plug them in. And once again, we said that energy here is 8.35 times 10 to the minus 19th. 8.35 times 10 to the minus 19th are your joules. Divided by Planck's constant right here, 6.63 times 10 to the minus 34th joules times seconds. And now we can go ahead and do the calculations. So we take 8.35 times 10 to the minus 19th. I'm doing the calculations on my calculator. Divided by 6.63 times 10 to the minus 34th. Is that what that says? My 34th looks like a 39th. And I end up with 1.26 times 10 to the 15th. So what I get in my calculator for the answer is 1.26 times 10 to the 15th. And you'll notice that joules here cancel with joules down here, leaving me with seconds in the denominator. So I end up with 1 over seconds as my units. And there is my answer. That's my frequency. 1.26 times 10 to the 15th waves per second, or I can even write it as 1.26 times 10 to the 15th. Oh, that's ugly. Let me get rid of that. Okay. Times 10 to the 15th hertz. That'll also work. Okay. So this is how we can calculate our frequency from our energy. And you will have to do that in tomorrow's worksheet. We're going to be looking at light and figuring out the energy that it has, and then wanting to know what frequency we've got it. So if you're given these last two samples, this equation can be used to do the following. If you're given frequency, you can calculate energy. If you're given energy, you can calculate frequency. Okay, that's the basic idea there. Okay, for problem number 3, we're going to look for something a little different. Well, we're actually looking for the same thing, but we're given a little bit different information. This problem right here says, calculate the energy, go ahead and do that. Calculate the energy in a photon with a wavelength of 5.85 times 10 to the negative 7th meters. Typical wavelength for visible light, roughly in the 10 to the negative 7 meters, or we call nanometers, and we'll do another problem with nanometers in just a little bit. We're looking for energy. The only equation we have with energy is E is equal to H times frequency. But we are given wavelength, and wavelength is lambda, right? Or at least that's what lambda is. So made that look like frequency. So this equation does not have lambda in it. But what we want to do is we want to, if we can figure out what the frequency is, then we can go ahead and solve for energy. Because remember, H is constant. So there's the second equation, C is equal to lambda times frequency. And that's what this is. It's wavelength, it's lambda. So what we can do is we can solve for the frequency here. Plug in wavelength. Remember that C is a constant, just like H is a constant. So if you can plug in wavelength, solve for frequency, then once you have frequency, plug it into here and solve for energy. That's basically what we're going to be doing. If this is a two-step problem. And so the first problem here, what we're going to be doing is we're going to be solving for frequency. And basically what you can do is rearrange this equation to either solve for frequency or wavelength, right? If you divide both sides by wavelength, divide both sides of this equation by wavelength, you get that it's always C divided by the other. So in this case, divide both sides by wavelength, you end up with C divided by wavelength is equal to frequency on the left side. And then I can rewrite that. I can just flip them around. Frequency is equal to C over wavelength. If you ever wanted to solve for, let's say, wavelength given frequency, you can also do it that way. I'll do it down here at the bottom here. C is equal to wavelength times frequency. If you want to solve for wavelength, divide both sides by frequency. You end up with C over frequency, C over frequency, C over frequency is equal to wavelength. So, and I just go ahead and just change the equation around. Wavelength is equal to C over frequency. That's one equation we get out of it, out of the main equation, and this is the second one. Okay. So we want frequency. We're going to take frequency, in order to get frequency, we're going to take C, the speed of light. Remember, C is a constant, it's always the same, 3 times 10 to the 8th meters per second, divided by the wavelength. And we're given the wavelength as 5.85 times 10 to the negative 7th, 5.85 times 10 to the negative 7th meters. Has to be in meters. If you're given any other centimeters, kilometers, nanometers, as we'll see in the next sample problem, you change it to meters, because that's what's going to happen, because these units and these units have to cancel with each other, so they cancel. And what you're going to get is the frequency of this problem. This right here is going to be, let me go ahead and get my calculator, 3 times 10 to the 8th divided by 5.85 times 10 to the negative 7th. And I get 5.13 times 10 to the 14th. So let me go ahead and write that down. 5.13. 5.13 times 10 to the 14th. Okay, that's my frequency. 10 to the 14th hertz. Because really the only thing that's left is 1 over seconds. So that's my frequency right there. That's not the answer. The answer is how much energy do I have? But that's my frequency. Okay, and we use this equation. We're not using this equation right now. If we were looking for wavelength, we'd use this equation, but we're not looking for that right now. Now, in order to get energy, all I have to do is use this other equation right here. Energy is equal to H times frequency. And remember that H is 6.63 times 10 to the minus 34th joules times seconds, multiplied by the frequency I just figured out right here, which is 5.13 times 10 to the minus, no, actually 10 to the 14th. That's not even a negative, it's positive. 10 to the positive 14th per second. Once again, just like we did in the last problem, the seconds cancel out, leaving us with joules. And I'm going to take 6.63 times 10 to the minus 34th. Let me do that in your calculator. 6.63 times 10 to the minus 34th, multiplied by 5.13 times 10 to the 14th, which is what we calculated as our frequency. And I get 3.40 times 10 to the minus 19. 3.40 times 10 to the minus 19th joules. And that is your answer right there. Okay, so in order to calculate the energy from a given wavelength, we have to, let me go ahead and change the color over here. I'm going to take it in blue. We have to take our speed of light and divide it by the wavelength. That's going to give us a frequency. Right. Then once we get a frequency, we can plug it into this equation, and that's going to take Planck's constant multiplied by our frequency, and that's going to give us our answer of energy in joules. Okay. Okay, let's do one last problem. In case I haven't mentioned, you guys should be doing the calculations that I done here and checking to see if you get the same answers. Sometimes some of the problems that people have on these problems, some of the hardest parts is trying to do the actual calculation in your calculator, because you got to put you'll notice, we just learned scientific notation, and you got to put these things in correct scientific notation, okay, so that they work out correctly. All right, let's go ahead and take a look at this one. What wavelength will a photon with energy 2.95 times 10 to the minus 19 joules have in nanometers? Actually, nanometers, these units right here, nanometers are very common because a nanometer is a billionth of a meter, and a lot of light, well, all of light actually is in a few hundred nanometers. So instead of saying, some 150 times 10 to the negative 7 meters, we just say nanometers. So let's go ahead and figure this out. Now, this equation wants wavelength. You're given energy. And so once again, we have the equation E is equal to H times frequency. And so we can put energy in there, but there's no wavelength in this equation. The other equation here, C is equal to lambda times frequency, and so this is the wavelength. This is what we want to find. So we want to solve for wavelength. We want wavelength is equal to C over frequency. I showed you how to turn that into the this equation, right? Which means that if we can solve for this equation, remember that C is a constant, so we already know that, that's 3 times 10 to the 8th meters per second. If we know the frequency, take C divided by the frequency, that gives us our wavelength. But we don't know it. Right now we're just given energy. Right? So we're given a number. Ooh, that was ugly. I know I have that box down here below it. We're given an energy, and we know that H is a constant, so that means we can solve for the frequency. And if I solve for the frequency, I divide both sides by H. I get that the frequency is going to be equal to E divided by Planck's constant. So I can get my frequency that way, then plug it into here, and that'll give me my wavelength. So let's do that. What happened here? Here, let me just take care of this real quickly. All right, that's an H down here. Should be an H. So our frequency is E over H because we're given energy. Our energy is 2.95 times 10 to the minus 19 joules. And I divide that by 6.63 times 10 to the minus 34th joules times seconds. Once again, I want to emphasize, this number down here is the same number we've been using over and over again. Right? this number down here, every time there's an H, we use the same number. It's a constant. It's always the same number. Some people get all confused. They're like, well, how do I know that what H is for this problem? It wasn't given to me. It is. It's always given to you. Both H and C are always given to you. They're always the same number. So let's calculate this out. We got 2.95 times 10 to the minus 19th is your energy, divided by 6.63 times 10 to the minus 34th, and that's going to give us 4.45 times 10 to the 14th. So our answer here is going to be 4.45 times 10 to the minus 4, no, not to the minus, 10 to the 14th per second. And once again, it's per second because joules cancel, leaving us seconds down in the denominator. Now this is our frequency. Now we can plug it into here. And so I'm sorry if I'm not going kind of down. I'm actually going to go back up because I have my equation here, and I'd like to use the bottom here for something else in just a little bit. All right, so in order to figure out the wavelength, lambda is the wavelength. What I do is I take my speed of light, 3 times 10 to the 8th. Once again, also, every time you see C, it is this number. It's a constant. That's why I put the little stars over them. Those guys are constants. Divided by the frequency. This is our frequency right here. So 4.45 times 10 to the 14th. Ugly, ugly, ugly. I will get this. 10 to the 14th per second. Okay. So that seconds cancel here. This is going to leave our answer in meters. So I'm going to take our 3 to the 8th, 3 times 10 to the 8th, divided by 4.45 times 10 to the 14th, and I'm going to get 6.74. 6.74 times 10 to the negative 7th. And our units will be meters because that's what the units were in the speed of light. So this here is our wavelength. But it doesn't answer the question fully, because it gives us a wavelength, and that's what we want. We want the wavelength, but we want it in nanometers. So we're like 90% of the way to finishing this problem. The only thing we have to do now is convert it from meters to nanometers. And you will recall, I'm going to move this up here just a little bit, that, let me see, the prefix nano means a billionth. So we know, and I'll put it over here so it's not right at the beginning, 1 meter equals to 1 times 10 to the 9th, which is a billion, nanometers. So 1 meter is equal to 1 billion nanometers. Nanometers are billionths of a meter. So all I have to do now is convert 6.74 times 10 to the minus 7 meters. Then I do the conversion factor. Sorry, ugly, ugly again. 6.74 times 10 to the minus 7. There we go. At least let me make that sort of steady. I want my meters to cancel out, so I'm going to put my 1 meter on the bottom. Then I want nanometers to remain, so I'll put 1 times 10 to the 9th nanometers on top. Meters cancel. And if I take 6.74 times 10 to the negative 7th, multiply by 1 times 10 to the 9th, what I get is 674. And the units are nanometers. Okay. And so there is my answer. There is my answer to this question up here. What wavelength will a photon with energy 2.95 times 10 to the minus 19 joules have in nanometers? It's right here, 674 nanometers. Okay. So, just to summarize real quick, I'm going to move this up here. There are 3 unknowns in these equations. There is energy. Oops, that's what I need here. Energy. There is frequency, and there is wavelength. If you're given frequency, you can turn it into energy by using the equation E is equal to H times frequency. And if you're given energy, you can turn that back into frequency by plugging it in here. Remember that H is a constant. So we never have to find what H is. H is always the same. So E, or if you know frequency, you'll know energy. If you know energy, you know frequency. And if you don't have that information, but you have wavelength, well, wavelength can be turned to frequency using the equation C is equal to frequency times wavelength. Okay. Now, once again, a reminder that C is a constant here, so you don't have to look for it. That's always the same. It's 3 times 10 to the 8th. So if you plug in wavelength, you can solve for frequency. If you plug in frequency, you can solve for wavelength. Okay. So if you're given wavelength, you can solve for frequency, which then you can solve for energy. If you're given energy, you can solve for frequency, which you can solve for wavelength. And if you're given frequency, you can solve for either also. Okay. So just want to make sure that people understood that. We're going to need these types of calculations to do the calculations with the atom tomorrow in our next lesson. Okay. So I hope this was helpful. If not, see me in office hours. We can go over any part of it.